In this video, we will learn about generative adversarial networks or GANs. And GANs are extensively used today for various tasks such as image synthesis, image-to-image translation, and so on. So let's dive right in.
Generative Adversarial Networks.
So in GANs, we're going to take a game theoretic approach where we're going to learn to generate from our training distribution through a setup of a two-player game. So in this GAN setup, what we want to be able to sample from is from a complex high-dimensional training distribution. So we want to produce samples from this distribution, and there is no direct way that we can do this. So we can have this really complex distribution and we cannot just take samples directly from it. So the solution that we are going to take is to sample from a simpler distribution, for example, random noise or Gaussians, which we can sample from very easily. So we are going to learn transformation from these simple distributions directly to the training distribution that we want, and we are going to use neural networks to represent this complex distribution. So we are going to take some input vector, which is a vector of some dimensionality that we specify of random noise. And then we are going to pass this through a generator network here, and then we are going to get a sample from the training distribution as the output. So for every input of random noise, we want to get a corresponding sample from the training distribution. So the way that we are going to train this network is that we are going to look at this as a two-player game where we have a generator network and a discriminator network. So the generator network as player 1 is going to try to fool the discriminator by generating these fake images, which are basically real looking images. And the second player, which is the discriminator network, is now going to try to distinguish between the fake images from the generator and the real images from the training data. So we have this random noise that is going into our generator network, which is then going to generate these fake images, and we also have real images from our training set. Now we want our discriminator to be able to distinguish between these fake images and the real images. So the idea here is that if we want to have a very good discriminator that is able to distinguish between real versus fake images, then if the generator network is able to generate these fake images that can successfully fool the discriminator, then we have a very good generative model, because now we are generating images that look very similar to the images from the real training set. Okay, so we're going to train these networks jointly in a Minimax game formulation. You can see the Minimax objective function here. So we are going to take minimum over theta g, which is a parameter of the generator network g, and the maximum over parameter theta d of our discriminator network. So if you look at these terms, the first one is the expectation over log of d of x, which is the discriminated output for real data x. So this is the likelihood of the real data being real from the data distribution P of data, while the second term here is the expectation of z drawn from P of z, which means that the samples from our generator, which means these are the samples from our generator network. And this term d of g of z is the output of the discriminator for the generated fake data. Here the discriminator wants to maximize this objective such that d of x is close to 1, which means that it is high for real data, and then d of g of x is close to 0, meaning that we want this to be small. So if you want to maximize this, it means that the discriminator is doing a good job between distinguishing between real and fake data. And basically, if we want to minimize the objective, such as d of g of z is close to 1, then basically the 1 minus sign here is small, and the discriminator thinks that the fake data is actually real. In other words, the generator is producing real samples. Alright, so now in order to train this, we are going to alternate between gradient ascent on the discriminator. So we are going to try to learn theta d, that is maximizing this objective, and then gradient descent on the generator. So this is how we train the GANs. We do gradient ascent on the discriminator and gradient descent on the generator. And we can basically alternate between training the discriminator and then the generator in this game, where the generator is trying to fool the discriminator. However, in practice, this generator objective actually does not really work very well. Alright, so if you take a look at the loss landscape to see why this happens, first the loss d of g of z, which is what we want to minimize for the generator. So the slope of this loss is actually going to be high towards the right that you see here, high when d of g of z is close to 1. So that means that when the generator is doing a good job of fooling the discriminator, we are going to have a high gradient. While if we have bad samples, when the generator has not learnt very well, this is when the discriminator can easily distinguish the generated samples, and it is not close to this 0 region on this x-axis. So here the gradient is relatively flat, which means that the gradient signal is dominated by the region where the samples are already quite good. So whereas what we wanted to actually learn a lot when the samples are bad. So in order to improve the learning, we can use this slightly modified cost function that you see here. So where we now do gradient ascent. So instead of minimizing the likelihood of the discriminator being correct, which is what we did before, now we are going to maximize the likelihood of the discriminator being wrong. So which is basically the objective of maximizing log of d of g of x. So we want to maximize this flip objective here, and we can see in this plot that basically we have a high gradient signal in this region on the left, and where we have bad samples, and now we have a flatter region towards the right where we have good samples. And this is basically the same objective as fooling the discriminator, but in practice, this works much better. Okay, so now let's take a look at the GAN training algorithm. So for each iteration of training, we are going to first train the discriminator network and then train the generator network. So for k steps of training, the discriminator network, we will sample a mini batch of noise samples from the noise prior Z, and we also sample a mini batch of real samples from our training data X, and we will then pass these noise samples through our generator, which gives us the fake images. So now we have a mini batch of fake images and a mini batch of real images. So and then we will take a gradient step on the discriminator and update the parameters of the discriminator, and we do this for a certain number of iterations, and after that we will move on for training the generator. So here we will sample from a mini batch of noise samples, and we pass it through the generator network, and we optimize the generator objective that we see here. So basically we are going to take these two steps alternatively. So on top of it, it says that we are going to train the discriminator for k steps. So this is the topic of debate. Some people train one step for the one step and then alternate, and some others find that taking k greater than 1 to work better. However, there has been some recent work that alleviates this problem, which is using Wasserstein GANs. And this is an example that does not basically have this problem. Okay, so once we have trained both the generator and the discriminator networks, we can now just take the generator network here and we can use this to generate these new images, and we take the noise input X, pass it through the generator network, and then generate these fake images. Alright, so now let's look at some generated examples from these GANs. On the left, you can see examples of training of MNIST, and on the right, you can see examples from FACES. And for each of these on the right, you can also see the nearest neighbor from the training set here. And we can see that it's able to generate very realistic samples, and it doesn't really directly try to memorize the training set. So here are some more examples from the CIFAR dataset from the original GAN paper from 2014, and we can see that these were not really that great at the point when these initial networks were initially introduced in 2014. So since then, there's been a lot of work on improving GANs. One of the important papers was from Alex Radford on using convolutional architectures with GANs. Previously, they only used fully connected networks. Here you can see some guidelines from Alex Radford's paper. You can take a look at this paper for more details if you're more interested on these guidelines. So here are some examples from of the work of Radford et al. We can see that the samples from these architecture training on real data of bedrooms, and here we can see that the samples are very realistic images of bedrooms, and these are just generated by the network. So these images don't really exist in the real world. All right, so the year of 2017 was really the year that pushed generative adversarial networks forward, and there are numerous papers from this year that significantly pushed the state of the art. So on the left here, you can see some work on better training and generation, and in the middle we see some work on source to target domain transfer. But here we are trying to go from a source domain of horses to a target domain of zebra. And here we are trying to go from apples to oranges and so on. And we can see that the generated fake samples are quite realistic here. There are also many other applications of GAN, such as text to image synthesis. So we give some text here and we want to synthesize images that describe the text. Another really famous example is basically this pix-to-pix architecture. These are almost these fundamental building blocks in many image translation tasks. So here we have these sketches that are hand-drawn, and from these sketches the networks learn to generate these images. On the bottom, what we can see is this Google Maps grid structure, and networks generate these satellite maps that correspond to these grid structure. So there are a lot of online demos of GANs, which are really cool. If you already don't know some of these examples, I urge you to take a look at some of them if you're interested. All right, so just in 2019 was another major important paper called Big GAN. So until then, what we saw before, all of them were trained on small images, and the training process was extremely sensitive to hyperparameters and specific augmentations to get good results. So then the Big GAN paper put these together to a suite of recent best practices for training GANs, and they also scale up the batch sizes and model parameters. So this enables us to generate both high resolution and high quality images. As you can see here, there are many more examples online from these Big GANs. Okay, so there's also this website that is called GANZoo that compiles a whole list of these papers. There are a lot more papers now than what we've shown here. So if you want to work on GANs, if you're interested to read about more of these new GANs, then take a look at this GitHub link with the paper that is shown here. All right. So let's now discuss the advantages and disadvantages of variational autoencoders and generative adversarial networks. Variational autoencoders often result in a blurry output image since autoencoders do not verify if the generated output is real or not. On the other hand, generative adversarial networks result in very realistic output images since the generator tries to fool the discriminator network by producing images which are difficult to differentiate from real samples. So the discriminator essentially controls that the results look very real and appealing. With variational autoencoders, we in fact have more control of the output since we can define the sampling from the latent space during inference. Therefore, it's possible to sample from a certain region of the latent space multiple times. For generative adversarial networks, it's not really possible to control the resulting output since two independent networks are included in the output generation, and the generator creates the result from random noise. However, generative adversarial networks incorporate the disadvantage that there is no guarantee for convergence. Actually, due to the two-player game, it could happen that the network diverges instead of converges. Due to this reason, the training of generative adversarial networks is a very interesting challenge. Alright, so this brings us to the end of this video. I have two questions for you. One is a repetition question. So while training a GAN, do we train the generator first or the discriminator first? So this is supposed to be, and why not the other way around? So an application of what you just learned is that, can you think of any other application domains where GANs can be helpful other than in computer vision tasks? So this is also the end of this lecture. We'll see you in the next lecture. Thank you.